Now we've seen stellar evolution usually ends up with a degenerate star. Either the core of the star is degenerate or the entire star will be degenerate. That means the equation of state, this is one expression of degeneracy, does no longer depend on temperature. We have a direct pressure density relation. Okay, once we have a pressure density relation, what does it mean? Well, we go the usual way, we estimate our differential equations. Then pressure, the hydrostatic equilibrium, which is of course also valid for degenerate stars. Pressure gradient has to balance gravity. In the Lagrangian form, dP by dmr is given by minus gm over r to the fourth, and we estimate this relation in the usual crude way. You replace the pressure gradient by P over M, and the right hand side will be proportional to M over R to the fourth. So the pressure goes with mass squared divided by the radius to the fourth. Now, if we have, well, of course, the density is also estimated in the usual way. The density is given by mass over the volume, or mass over R cubed. Well, what does it mean if we have a pressure density relation? The pressure may be expressed in terms of M over R cubed, and then we have a relation from the hydrostatic equilibrium, well, which also depends on the mass and the radius. So what do we end up with? With a relation between mass and radius. So typical for degenerate equation of state is that we end up with a mass-radius relation. By assuming hydrostatic equilibrium, then we express the pressure in terms of mass and radius. Pressure-density relation gives us a relation between pressure, mass over R cubed. Therefore, we have the only parameters left in the relation is mass and radius, and we are left with a mass-radius relation. So if we assume the equation of state for non-relativistic fermions, for instance, non-relativistic electrons, then we have seen that the pressure goes with a density to 5/3, and once we insert this relation into our pressure, mass, radius relation, density, mass, radius relation, it's perhaps nice if you do it as an exercise. Simply take these relations, assume a pressure density relation of that form, and you will end up with a mass radius relation. Do you remember the mass radius relation you have seen yesterday in Professor Yadav's pun? Yes, the radius goes for a normal star goes with m2, well, roughly 1. The radius increases with mass. What we see here, what does the radius do with mass? For a degenerate star, it decreases with mass. So if we put mass on a degenerate star, which is described by this equation of state, then the radius will decrease once we add mass to it. Well, what will be the consequence once we decrease? Well, I have to say there are of course stars which satisfy this mass-radius relation and which are very nicely described by the equation of state of a non-relativistic degenerate gas. They obey this mass-radius relation. These are the white dwarfs. Probably all of you who have studied a little bit of astrophysics came across the white dwarfs. These are degenerate stars, and the mass-radius relation is R proportional to mass to minus 1/3. Okay, now once this is the mass-radius relation for non-relativistic fermions, we may ask what will be the mass-radius relation for relativistic fermions. Relativistic fermions would be those characterized by an equation of state where the pressure goes with a density to 4/3. So let's take this pressure density relation and ask what is the mass radius relation. Well, what we end up with, the mass has to be constant here. So if the equation of state is given by relativistic electrons, then the mass radius relation will no longer be a relation between radius and mass, because the radius cancels. You can convince yourself simply by inserting this relation, and you will find radius is no longer a parameter of the relation, but the mass is actually a constant. What does it mean? If we have a configuration or a star which is characterized by this equation of state, it means there is only a single mass possible. What happens if the mass is smaller than this value? Well, if it's smaller than this value, then gravity will be smaller than in the case of this constant mass given here. So gravity will be smaller and pressure will push it back to a region where possibly, we'll come to this in a moment, will push it back so the star will expand. If the mass is bigger than its value, then the gravity will always be bigger than the pressure gradient, the star will collapse. So there is a single mass which is possible for equilibrium. Any other mass will not be in equilibrium. Okay? There is a constant mass which is determined by the constants which are appearing in the equation of state and in the equation for hydrostatic equilibrium. Here, the radius is a function of mass. It shrinks once mass is increased, and here we have only one equilibrium configuration which needs to have a very well specified mass. If the mass is smaller, the star will be expanding, no equilibrium possible. If the mass is bigger, the star will contract. Okay, this constant mass or this unique mass is called Chandrasekhar's mass, and it has been found, or it has been defined the first time by Chandrasekhar, who considered in detail all these degenerate stars. Actually, I have to perhaps add a historical remark, because Chandrasekhar was considering the case or the possibility that stars might be described by a degenerate equation of state. And those days he worked together, or was a student of Eddington in Cambridge, and Eddington strongly objected against his ideas. Even the sad thing about this, it was even a personal offense against Chandrasekhar. Eddington did those time, and Eddington never believed what Chandrasekhar did, but the case or the consideration of degenerate equation of state is essential for stellar physics. Now, well, Chandrasekhar got Nobel Prize much later than his discovery. So it's now recognized, of course, that he was right and Eddington was wrong. But he must have had a very hard time together with Eddington, because Eddington was obviously not very nice to him. So you see, without degeneracy, we would not be able to stop stellar evolution. We would get a infinite temperature. That was the case before. So if degeneracy would not be there, we would have an entirely different stellar evolution. And Eddington, Chandrasekhar, in a natural way explained the mass-radius relation for white dwarfs. So he described this correctly, and he invented, or he gave this limiting or unique mass, which is obtained once pressure goes to with density to 4/3 for the relativistic fermions. So what is the meaning of this constant mass, and what is the meaning of Chandrasekhar's limit? Now consider a sequence of white dwarfs. Let's have a sequence of white dwarfs, and let's increase the mass. Once we increase the mass, well, the density would increase if the even if the radius would be constant, but the radius decreases with mass, with minus 1/3. So in any case, mass increase leads to the increase of the density. Well, this implies that also the number densities of the electrons increases. Of course, charge neutrality would require that also the number density of electrons would increase. That means number density of electrons is proportional to, if in terms of the Fermi momentum, the maximum momentum in the distribution of our electrons, once it's completely degenerate, we have P naught squared is proportional, P naught is proportional to number density of electrons to 1/3. Okay, so this means that the Fermi momentum will increase due to the increase of the number density, so Fermi momentum goes up, and then of course also the energy of the particles will increase. Energy, the maximum energy for relativistical particles is proportional to P naught squared over 2m. So if we have an increase of the Fermi momentum, also the energy of the particle will increase. So if this process goes on for a sufficient time, well, we will have then an increase of the energy until the relativistic domain is reached. Here we have the classical non-relativistic particles, and once we increase the mass and the epsilon goes up, then ultimately we will reach the state where epsilon becomes relativistic, or the energy has to be considered to be relativistic energy, and therefore the electrons will become relativistic. So we have, with increasing mass, we have a transition from non-relativistic to relativistic degeneracy, and therefore a transition from an equation of state going proportional to rho to 5/3 to the equation of state where the pressure increases with rho to 4/3. Well, if we end up with relativistic degeneracy, we know that this requires, or there's only one mass for which equilibrium can be maintained. Okay, if this mass is smaller than Chandrasekhar's limit, what will happen? The star will expand, and it will come back to a less dense region, so it comes back to the non-relativistic region. So if we end up piling up material, if we end up with a mass which is equal to Chandrasekhar's limit or a little bit above, then the star will collapse. So this is actually the maximum mass for white dwarfs. If we add mass onto a white dwarf and we make this thought experiment, then the Fermi momentum, the number density of electrons will increase, the Fermi momentum will increase, the energy will increase until the electrons become relativistic, and then we enter the domain of relativistically degenerate electrons. Therefore, we have only one particular mass for which we can have equilibrium. If the mass is smaller, it goes back to the non-relativistic regime because it expands. If the mass is just the Chandrasekhar's limit or a little bit above, it will collapse. So this gives rise to a very well-known phenomenon in astrophysics. This is the cause or the onset of so-called supernova explosions. Actually, this thought experiment is done in a scenario which leads to supernova explosion. For instance, if our white dwarf is in a binary system and we companion sheds mass on the white dwarf, then it increases its mass. This is actually the process which is found in binaries. The companion sheds mass on the white dwarf, thereby its mass increases, and thereby the white dwarf finally reaches Chandrasekhar's limit. What happens then is a collapse, and the consequence is a supernova of type 1a. The supernova of type 1a are nice candles in the universe because their initial condition, essentially the initial condition, is the same for all of these processes. There's just one single mass which can be at the onset of this collapse. Therefore, these supernovae of type 1a are thought to run all in the same way, because the mass this unique mass is always the same. The initial conditions are the same. Therefore, also the following evolution of the supernova 1a explosion should be similar. That means their maximum brightness should be the same, and so they can be used as for standard candles. Once the brightness of them can be assumed to be the same, you can use that in different distances, and then by comparison again with the apparent luminosity of the supernova of type 1, we can determine the distance. So the supernovae of type 1 are standard candles for the measurement of distances. The reason for them to be standard candles, or the main reason for them to be standard candles, is that the initial mass before collapse is Chandrasekhar's mass. Question: why do they explode? Well, there have been white dwarfs onto which material has been put. Well, white dwarfs are the leftovers from stellar evolution. Well, this might be white dwarfs which contain carbon and oxygen, because carbon and oxygen burning has not been reached. So the interior of these white dwarfs may consist of carbon and oxygen. There are helium white dwarfs, these are white dwarfs which have ended their life, or which have become degenerate before carbon burning, before helium burning is ignited. So there is a variety of white dwarfs: helium white dwarfs, carbon oxygen white dwarfs, neon magnesium white dwarfs, and so on. So what happens is, well, if the star collapses, it's a degenerate star which collapses, then there is still nuclear fuel left which could be burned, because we have not yet reached the iron stage, so there is binding energy per nucleon left. So the remaining helium, carbon, oxygen, neon, magnesium can be ignited, and therefore this could release nuclear energy. This is done under degenerate conditions. Degenerate conditions, I will not go into the detail, means that there is a runaway, a thermonuclear runaway, because the temperature does not react on, or the star does not react on temperature increase, because the pressure is made up by the electrons. Pressure is, during this collapse of the white dwarf, is maintained by the pressure of degenerate electrons. Now the nuclei are compressed, temperature goes up, and they will start to ignite helium burning, carbon oxygen burning under degenerate conditions. But the star will not react on the temperature increase, because the pressure does not feel the temperature, the electrons maintain the pressure. It means that the released energy will enhance the temperature even more, and we get a thermonuclear explosion or thermonuclear runaway. So the end of the evolution will be a total disruption of the star. Supernova of type 1a are thermonuclear explosions initiated by collapse, starting with Chandrasekhar's mass. The star is disrupted by a nuclear explosion. So this is one of the scenarios by which a star can end its life. That's where the degeneracy of the degeneracy comes in. Another scenario which has to do with the degenerate core is the supernova explosion, supernova of type 2, what we are talking about. We are supernova of type 1a in a binary system, thermonuclear explosions. They still have unburned nuclear fuel left. This is not true once a star has reached silicon burning and leaves behind an iron core. There is no nuclear fuel left because the iron has the highest binding energy to nuclear. In that case, once the nucleus of a massive star, the star has to have more than about 10 solar masses initially, then we will end up with a degenerate iron core. This degenerate iron core becomes bigger because silicon burning on top of the iron core will lead to an increase of the mass of the iron core. So silicon burning results in iron group elements as the ash will become bigger and bigger, and so the mass, similar to the white dwarfs, on which the mass is shed by a companion, the mass of the iron core within a massive star will increase and then ultimately reach Chandrasekhar's mass and collapse in the same way. So the essential process reaching Chandrasekhar's mass is the same both for supernova of type 1 and type 2, but in one case it's caused by a companion shedding mass on the white dwarf. For very massive stars, it's simply the increase of the iron core by the superimposed silicon burning shell, which adds mass to the iron core. But what happens then? There is obviously no nuclear fuel left. It cannot burn exothermically. It forms finally, during the collapse, it forms a neutron star. The envelope falls down onto the neutron star and is repelled, and then by a shock wave, the entire envelope is expelled and a neutron star is left behind. So in any of these two processes, Chandrasekhar's mass plays an important and the decisive role here. Okay, so this process, both in very massive stars forming iron cores or in binaries where white dwarfs get mass from their companion, Chandrasekhar's mass plays a decisive role. Okay, this is the basis of supernova, collapse, and explosion. Did I forget something? No. Okay. Okay. So finally, this should close our digression into stellar evolution. Essentially, I have left one chapter on semi-analytical stellar models. That is done because we will resort to these models also in considering stellar pulsations. We will use them as toy or idealized models to study stellar pulsations. These are the polytrops. And how much time do I have? 5 minutes. So let me just introduce what polytrops are. Polytrops are stellar models which are based on the assumption that pressure only depends on density. In a particular form, well, pressure depends on density in the form of a power law. Pressure is given by a constant times rho to some power, and the power is usually written in terms of 1 plus 1 over n, where n is called the polytropic index. So it's very similar to what we considered before for the case of degenerate, non-relativistic and relativistically degenerate stars. It is the construction of a stellar model with prescribed pressure-density relation. It does not mean that the pressure-density relation, or does not mean that the equation of state has to have this form. This pressure-density relation may be caused also by a particular way in which energy is transported, plus the equation of state. We'll see that in a moment. So it's a formal way to describe pressure-density relation without any reference to the temperature. It's a formal way to close the system of equation. What we do once we assume a pressure-density relation, what is achieved then? What about energy transport? What about energy equation? We get rid of that, because once we assume that pressure and density are related, we decouple the thermal equation from the mechanical equations, and so to say, we close the system of the mechanical equations by assuming this polytropic relation. So far it's just a formal relation, and the question is, when is this relation justified? Well, one justification would be, the case we discussed a few minutes ago, if the equation of state is itself containing a pressure-density relation, for instance in the case of degenerate electrons, relativistically or non-relativistically degenerate electrons. This is one case which is covered by this formal relation between pressure and density. Another way to realize such a relation would be if the energy transport would be very efficient. Very efficient energy transport would mean temperature is constant. This is not met in stellar environments, but let's assume we have extremely efficient energy transport, then the final state will be temperature is constant, and once we have an equation of state for an ideal gas, then we would have P is proportional to rho times T. If T is constant, then P, the pressure, would be a function of the density only. Another way of obtaining such a relation between pressure and density would be to assume that the nabla, that the logarithmic logarithmic derivative of temperature with respect to pressure is equal to the adiabatic value. Nabla, keep in mind, is the value of d log T by d log P, which is actually achieved in a star. To define this, you need to have a temperature stratification, a pressure stratification. You have to compare them to derive or to define the nabla. So this is based on a real stellar model, needs a stellar model to be defined, and nabla adiabatic is determined on the basis of thermodynamics only. You don't need to refer to a stellar model to determine nabla adiabatic. What happens then? Efficient convection. We discussed that. If the convection transports energy efficiently, then we know then nabla will be close to the adiabatic value. Or in other words, that within the star we have a constant entropy. Nabla equal to nabla adiabatic means that the entropy is constant. Once we write pressure as a function of density and entropy, then this means entropy is constant, and we are left with a relation between pressure and density alone. So in any of these cases, we end up with a pressure-density relation. Keep in mind, it's not necessarily that the equation of state gives a pressure-density relation, but energy transport together with the equation of state may also give a formal relation between pressure and density. So there are applications of this polytropic relation to stellar models. Okay, so one question: where is this condition met? Do you remember? Pardon? No, this condition. Which stars can be described by nabla equal to nabla adiabatic? I've mentioned it probably only very shortly. Once we consider the Hertzsprung-Russell diagram, there is some imaginary line on the right hand side. This is the Hayashi track. And actually you can calculate the Hayashi track by calculating models which are described by nabla equals to nabla adiabatic. So you can use polytropic theory to define the Hayashi line at the right hand border in the Hertzsprung-Russell diagram. So this has actually applications. For instance, the Hayashi line would be an application of the polytropic theory. Okay, so we have introduced this formal relation between pressure and density. And we have justified why we should, or why we could describe at least some situations by this pressure density relation. In some sense, both equation of state and the thermodynamics energy transport are, so to say, condensed in a pressure density relation. So we assume that we can replace the thermodynamics simply by this formal pressure density relation. The question now is, what is the consequence? How can we solve the equations, and how do the solutions look like? So we will continue this after.